If you have been planning to upgrade your PC storage, to add an NVMe SSD for faster game loading, larger video projects, or simply more space for your expanding file library, you need to understand what is happening in the flash memory market right now. After years of falling prices that made high-performance solid-state storage accessible to mainstream users, the market is shifting. NAND flash manufacturers are cutting production. Enterprise demand is surging, driven by AI infrastructure build-outs. Supply chain dynamics are tightening. And the result is that storage prices, which fell consistently for over a decade, are beginning to rise. Industry analysts are warning that depending on how supply and demand dynamics evolve, we could see significant price increases over the next 12 to 18 months. Not overnight, not universally, but enough that the terabyte NVMe drive you can buy today for $100 might cost substantially more next year. The question facing anyone who depends on fast, affordable storage is whether to secure capacity now or wait and hope prices stabilize. Because unlike CPUs and GPUs where you upgrade for performance, storage is something you need more of constantly. And if prices rise significantly, expanding storage becomes a luxury rather than a routine upgrade. Understanding what is driving these market changes and what they mean for your computing needs requires examining the complex global industry that produces the chips inside your SSDs. To understand why NVMe SSD pricing matters, you must first understand what these drives are and why they have become essential to modern computing. NVMe, or Non-Volatile Memory Express, is a protocol designed specifically for solid-state storage connected through PCIe, the peripheral component interconnect express bus that also handles graphics cards and other high-speed components. This represents a fundamental architectural improvement over older storage interfaces like SATA, which was designed for mechanical hard drives decades ago and became a bottleneck for solid-state storage. The performance difference is dramatic. A SATA SSD maxes out at approximately 550 megabytes per second, sequential read and write speeds, constrained by the SATA 3 interface's 6 gigabit per second bandwidth limit. An NVMe SSD using PCIe 3.0 can achieve 3,500 megabytes per second or higher. PCIe 4.0 NVMe drives reach 7,000 megabytes per second. The newest PCIe 5.0 drives are pushing past 10,000 megabytes per second. This is not incremental improvement. This is order of magnitude performance transformation. For gaming, NVMe drives reduce load times dramatically, eliminate texture streaming stutters, and enable new game design paradigms where massive open worlds load seamlessly without hidden loading screens disguised as corridors or elevators. Modern game consoles, the PlayStation 5 and Xbox Series X, use custom NVMe storage as foundational architecture, and PC games are increasingly designed assuming NVMe performance characteristics. Content creators working with 4K or 8K video depend on NVMe drives for real-time editing. Scrubbing through high-resolution footage requires streaming hundreds of megabytes per second from storage to RAM. NVMe provides the bandwidth that SATA cannot, enabling smooth editing workflows that would be impossible on older storage technology. AI and machine learning workloads increasingly common on consumer hardware as AI features are embedded into productivity software, photo editing, video processing, and even operating systems. Benefit from fast storage for loading large datasets and model files. The difference between waiting seconds versus minutes for model loading compounds across hundreds of daily operations. General system responsiveness improves with NVMe. Application launches, file searches, system updates all feel instantaneous on NVMe compared to SATA or mechanical drives. Once you experience an NVMe-based system, returning to SATA feels intolerably slow. This is why NVMe has transitioned from enthusiast luxury to mainstream expectation. Every new laptop and desktop motherboard includes M.2 slots for NVMe drives. SATA is becoming legacy technology. Demand continues growing because storage needs grow. Modern games exceed 100 gigabytes. Many exceed 200. Professional video projects in 4K consume terabytes. Photo libraries from high megapixel cameras expand endlessly. Users accumulate data faster than they delete it. The median storage capacity in new PCs has grown from 256 gigabytes a few years ago to 512 gigabytes today, with 1 terabyte becoming standard in mid-range and higher systems. This growth drives continuous NVMe demand. Understanding potential price increases requires examining the NAND flash production industry, a complex global market dominated by a small number of manufacturers who collectively determine supply. NAND flash memory, the storage medium inside SSDs, is produced by approximately 6 major manufacturers: Samsung, SK Hynix, Micron, Kioxia, Western Digital, and Intel, though Intel has largely exited the NAND business. These companies operate massive fabrication facilities requiring billions of dollars in capital investment and years to build. Production capacity cannot be increased quickly in response to demand spikes. The economics of NAND production are brutal. Manufacturing is capital intensive with thin margins during periods of oversupply. When too much NAND is produced relative to demand, prices crash. Manufacturers lose money. They respond by cutting production, idling fabrication lines, and delaying expansion plans. This reduces supply. Eventually, demand catches up to constrained supply, prices rise, manufacturers become profitable again, and they invest in expanding capacity. This cycle repeats perpetually. From approximately 2017 through 2023, the industry experienced sustained oversupply. NAND prices fell consistently year over year. A 1 terabyte NVMe SSD that cost $200 in 2019 could be purchased for under $50 by 2023 in some markets. This collapse in pricing benefited consumers enormously but devastated manufacturer profitability. Multiple companies reported losses in their NAND divisions for consecutive quarters. The response, announced publicly through earnings calls and investor presentations, was production cuts. Manufacturers idled older fabrication equipment, delayed new fab construction, and reduced wafer starts, the number of silicon wafers entering production. These production cuts are deliberate supply management to restore pricing power and profitability. The manufacturers are not subtle about this. They explicitly state in public filings that production is being cut to reduce supply and increase prices. This is legal and economically rational from the manufacturer's perspective, though it directly harms consumers through higher prices. Simultaneously, enterprise demand has surged. The explosion of AI infrastructure, massive data centers built by technology companies to train and run large language models and other AI systems, requires extraordinary amounts of high-performance storage. Training runs for advanced AI models can consume petabytes of storage. Inference serving, running trained models to respond to user queries, requires fast storage for model loading and result caching. Enterprise SSDs, particularly high-endurance drives designed for data center workloads, command premium prices and are more profitable for manufacturers than consumer drives. When manufacturers allocate production capacity, enterprise orders take priority over consumer markets. Geopolitical factors add uncertainty. NAND manufacturing is concentrated in South Korea, Japan, Taiwan, and to a lesser extent, the United States. Any disruption to these regions, whether from natural disasters, political instability, or international conflicts, could impact production. The ongoing tensions around Taiwan, where some NAND production occurs, introduce risk premium into long-term supply forecasts. Currency fluctuations affect pricing. NAND is priced in US dollars globally, but production costs occur in local currencies. When the dollar strengthens against other currencies, NAND becomes more expensive in non-dollar markets. When the dollar weakens, dollar-denominated prices may rise to maintain manufacturer margins. Technology transitions introduce supply constraints, and the industry is transitioning to more advanced NAND architectures, moving from 3D NAND with 128 or 176 layers to 200-plus layer designs. These transitions require retooling fabrication equipment, qualifying new processes, and ramping production yield. During transition periods, overall production capacity temporarily decreases as older production lines are converted and new processes are debugged. The impact of rising storage prices will not be distributed evenly across user segments. Different groups face different vulnerabilities and have different options for mitigating cost increases. Gamers building or upgrading PCs face direct impact. Modern gaming often requires 1 or 2 terabyte NVMe drives to comfortably hold a game library alongside the operating system and applications. If a 2 terabyte drive currently costing $100 rises to $150 or $200, that is a significant percentage increase in total system build cost. For budget builders, this could force compromises, choosing smaller capacity or slower SATA drives, both of which degrade the gaming experience. PC builders and system integrators purchasing components at volume face margin pressure. If they have committed to system prices but storage costs increase after commitments are made, they absorb losses or must renegotiate pricing with customers, damaging relationships and competitiveness. Laptop users have less flexibility than desktop users. Laptops often have soldered storage or single M2 slots, making upgrade difficult or impossible. Users who purchase laptops with minimal storage expecting to upgrade later may find that upgrade prohibitively expensive. Manufacturers who configure base models with 256 gigabyte drives, knowing users will pay for upgrades, can maintain or increase upgrade pricing if market prices rise. Content creators who archive large projects on affordable storage face ballooning costs. A videographer might currently archive completed projects on external NVMe drives that cost $80 per terabyte. If costs double, archival storage budgets double, forcing difficult choices about what to keep and what to delete. Businesses refreshing desktop fleets or upgrading server storage face budgetary impact. An IT department planning to upgrade 500 employee workstations with 1 terabyte drives sees costs increase by tens of thousands of dollars if per drive prices rise significantly. Enterprise budgets are less flexible than they appear, and unplanned increases in component costs force delays or cutbacks elsewhere. Data hoarders and home server enthusiasts building NAS systems with multiple drives face multiplicative impact. A 4-drive NAS storage build could ski. Costs increase by hundreds of dollars if per drive prices rise substantially. These users often operate on fixed budgets and must reduce capacity plans if prices rise. Conversely, some groups are largely insulated. Users with sufficient storage who do not plan near-term upgrades are unaffected. Enthusiasts who already invested in high-capacity drives benefit from appreciating asset value. Enterprise organizations with pre-negotiated volume contracts have short-term price protection. The question of whether to purchase storage immediately or wait is not answerable with universal advice because the correct decision depends on individual circumstances, risk tolerance, and storage needs. The case for buying now centers on price protection. If analysts are correct that prices will rise significantly over the next year, purchasing at current prices locks in savings. Storage does not spoil. NVMe drives have shelf lives measured in years even without use. Buying a drive now and holding it for a future build or upgrade, if you are confident you will need it, protects against future price increases. Current prices, in historical context, remain near all-time lows. Despite recent upticks, NVMe SSDs are still extraordinarily cheap per gigabyte compared to pricing from even 3 years ago. If this represents the bottom of the market cycle, buying at the bottom makes economic sense. Storage is a component you will eventually need more of. Unlike upgrading from a perfectly functional CPU or GPU where the upgrade is optional and performance-driven, storage expansion is often necessity-driven. When you run out of space, you must add more. Pre-purchasing storage you know you will need eventually at today's prices ensures against tomorrow's potentially higher prices. However, the case for waiting is also rational. Price predictions are uncertain. Analysts have been wrong before. The storage market is volatile and unpredictable. Well, past price increases have sometimes reversed as manufacturers brought additional capacity online faster than expected or as demand softened. Committing capital to storage purchases based on predictions that may not materialize represents risk. Opportunity cost matters. Money spent on storage now is money unavailable for other purchases or investments. If prices do not rise as predicted, you will have tied up capital earning no return when you could have waited and bought at similar or better prices later. Technology advancement continues. Waiting allows access to newer, faster drives. PCIe 5.0 drives are still maturing. 6 months from now, PCIe 5.0 drives may offer better performance at similar prices to PCIe 4.0 drives today. Buying now locks you into current generation technology. Storage needs are difficult to predict accurately. Purchasing capacity you think you will need but end up not using for years wastes money that could have remained liquid. Needs change. New cloud storage options emerge. Compression technologies improve. What seems essential today may be unnecessary tomorrow. A balanced approach for most users is to purchase storage you need for projects or upgrades planned within the next 6 months. If you are building a PC next month or need to expand storage imminently, buy now because you need it, regardless of price trends. If your current storage is adequate and you have no immediate plans requiring more, waiting remains reasonable unless prices begin rising sharply, at which point reassess. For users with moderate risk tolerance and budgets allowing speculative purchases, buying one additional drive beyond immediate needs as insurance against price increases is defensible. If prices rise, you saved money. If they do not, you have storage you will eventually use anyway. Avoid panic buying multiple drives based purely on fear of shortages or dramatic price increases. Industry predictions are uncertain, and excess purchases represent capital inefficiently deployed. Looking beyond immediate pricing concerns, storage technology is evolving rapidly in ways that will reshape computing over the next several years. PCIe 5.0, NVMe drives represent the current cutting edge, offering theoretical bandwidth exceeding 14,000 megabytes per second. Real-world drives achieving 10,000 to 12,000 megabytes per second are entering the market. This performance is extraordinary, but benefits primarily workloads that already saturate PCIe 4.0 bandwidth. For most consumer tasks, the difference between PCIe 4.0 and 5.0 drives is imperceptible. The more significant advancement is capacity scaling. Drive capacities at consumer price points continue growing. 2 terabyte drives have become affordable mainstream options. 4 terabyte drives are approaching prices that were unthinkable several years ago. 8 terabyte consumer NVMe drives exist, though at premium pricing. This capacity growth allows users to consolidate storage, reducing the number of drives needed. AI-driven storage demands will influence future development. As local AI processing becomes more common, storage requirements for AI models, datasets, and output expand. Operating systems with integrated AI, applications using local large language models, and creative tools generating AI content all require substantial local storage. This drives both capacity and performance requirements upward. Enterprise and data center innovations eventually trickle down to consumer markets. Technologies like computational storage, where processing occurs on the drive controller itself rather than requiring CPU involvement, improve efficiency. Multi-actuator designs and advanced error correction extend drive lifespan and reliability. These technologies debut in expensive enterprise products, but become cost-effective for consumer markets over time. Solid-state storage alternatives are being researched. Emerging non-volatile memory technologies like 3D XPoint, marketed as Intel Optane, offered performance between DRAM and NAND, but failed to achieve widespread adoption due to cost and limited capacity. Research continues into resistive RAM, phase change memory, and other exotic storage technologies that could eventually supplement or replace NAND flash. However, none are currently competitive with NAND on cost per gigabyte, and commercialization timelines remain uncertain. The fundamental question is whether storage will remain affordable for mainstream users. The industry trend toward fewer manufacturers with greater consolidation raises concerns about competition and pricing power. If supply remains concentrated and manufacturers coordinate production cuts to maintain prices, consumers face persistently higher costs. Regulatory scrutiny of potential anti-competitive behavior exists, but has not yet resulted in meaningful intervention. Conversely, technological advancement continues driving cost down over long timeframes. NAND flash cost per gigabyte has fallen exponentially over decades, despite cyclical price fluctuations. Betting against long-term technological progress and economies of scale has historically been wrong. The current price pressures may be cyclical rather than structural, resolving as production capacity expands and competition intensifies. Storage has evolved from a forgettable PC component, something you bought once and forgot about, into one of the most critical determinants of system performance and usability. The difference between mechanical hard drives, SATA SSDs, and NVMe is not incremental. It is transformative. And because modern computing, gaming, content creation, AI workloads depends fundamentally on fast storage, anything that threatens the accessibility and affordability of high-performance SSDs threatens the accessibility of modern computing itself. The current market dynamics, production cuts, enterprise demand surges, supply chain uncertainties create genuine risk that NVMe drive prices will rise substantially over the coming year. This is not guaranteed. Markets are unpredictable. Analyst forecasts are frequently wrong. Manufacturers may increase production faster than expected. Demand may soften. New entrants may disrupt pricing. But the structural factors driving prices upward are real, documented, and acknowledged by manufacturers themselves. For users, the decision is not whether storage matters. It does. The decision is whether the risk of future price increases justifies purchasing now versus waiting. That calculation depends on individual needs, budgets, and risk tolerance. There is no universal right answer, but what is certain is that understanding hardware market dynamics, recognizing when component prices are historically low or high, and making informed purchasing decisions based on that understanding is becoming as important as understanding specifications and performance benchmarks. Because in a market where prices can double within a year, buying at the wrong time can waste as much money as buying the wrong product entirely. Storage technology will continue advancing, capacities will grow, performance will increase, new interfaces and architectures will emerge. But whether those advancements remain accessible to mainstream users at prices that make high-performance storage a standard expectation rather than a luxury depends on market forces largely outside user control. And that should concern anyone who believes that the tools of modern computing, the ability to store and access information quickly, to create without constraints, to build systems without budgetary barriers, should remain accessible to everyone, not just those who can afford artificially inflated prices maintained by a small number of manufacturers protecting their profit margins. The question is not whether to secure your NVMe before prices potentially rise. The question is whether affordable storage will remain a right of modern computing, or become a privilege reserved for those willing to pay whatever the market will bear.